Wind energy makes up 30% of the UK's electricity demand, and here in Denmark that figure is a whopping 59%. But it has its drawbacks. It's a notoriously unreliable way of generating electricity, working only under certain weather-dependent conditions. That's why I want to explore how we can predict the power output of a wind farm based on the speed of incoming wind.
So let's jump straight into that. Classical mechanics gives us the equation power equals force times velocity, or power equals force dot velocity for vectors. Well, from the group project, we already have the speed of wind and the force applied to the wind at the same grid points. Since the forcing profile describes the force on each point in the domain, it is in effect a force density. Taking the scalar product of the force with respect to the speed of the wind at each grid point will therefore give us the power density of each grid. And summing these over the domain will give us the total power generated by the farm. Analytically, we could increase the number of grid points to infinity, giving us the formula power equals the integral over the domain of fx of xz times u of xz. But computationally, we'll stick with summing over our finite grid points. You'll notice that we have a constant mu to account for the imperfect efficiency of the turbines, and that the formula only contains u and not w, because the force only acts in the x direction. Now we have a method for calculating power output. Let's see how it changes with initial velocity of the wind. Okay, so according to this model, power scales linearly with velocity. Also, we can still generate power with zero velocity. This doesn't seem right. And indeed, we have another equation that confirms my suspicions, the wind power equation, which states that power equals half times efficiency coefficient times air density times rotor area times, most importantly, velocity cubed. So what went wrong? Well, we have to go back to the original forcing profile. As you can see, it's not dependent on wind velocity at all. Fx of xz equals minus a times u naught minus u of x naught z naught squared times the Gaussian terms is a more realistic forcing profile. The new term, u naught minus u of x naught z naught squared, where u of x naught z naught is the speed of the wind at the turbine hub, introduces an additional factor of u naught squared, meaning with this forcing profile, we would expect power to scale with initial velocity cubed, matching the wind power equation. But because of this, u and fx have become coupled. You can't get u without fx, and vice versa. To solve this, we can use an iterative scheme. Start with an estimate for the speed of the wind at the hub to define fx, then solve for u and get a better estimate. The scheme converges quickly, as detailed in the report. Now we have a more realistic model. We can try again to see how power scales with velocity. This already looks much better, going through 0, 0, and having a seemingly cubic shape. A simple log-log plot alongside a cubic confirms that our new model is able to produce the relationship between power and velocity that we observe. The last remaining question is, why should we calculate power output in this way? More specifically, can we not just use the wind power equation? Well, we've basically already explored the answer. By using such a general equation, P equals F dot V, we can make Fx as specific as we like, something we've already seen. We could take our expression for F even further, including factors like temperature and atmospheric pressure. The wind power equation, though simple and easy to use, is too restrictive. The only freedom to expand on it lies within the efficiency coefficient. So for complicated systems, for example where multiple turbines interact, it is not as useful as our preferred method.